Yeah, so before we start, so I am Lohith. I have been working in search for almost 5.5 years in an industry for about 11 years. So I'll just give a quick intro about Rohan as well. Any guesses about Rohan? He just passed out of college. Okay, so we were working on a project in the company. So it's about the learnings in that company is what we wanted to share with you. What are the best ways? What are the different use cases? How can you handle different things while building a rack pipeline is what we'll talk about.
okay, so I'll give you a very basic example, right? So let's say you have a word called king and queen, right? And you have attributes. Let's say an attribute is male, is female. So your king gets 1 for is male and 0 for is female. So in a two-dimensional graph, the king gets a vector of 1, comma 0, and the queen gets a vector of 0, comma 1, right? It's a very basic example, but think of it on a very large scale, where these machine learning models are trained on, let's say, trillions of data, right? And they sort of self-learn and figure out what's the best, most optimal number is for a sentence. Or let's forget a sentence. Let's just think about a word. What's the most optimal vector is for a word, right? So this is like a very high level of how these things are trained. Like I mean, this is a very big, complex topic, but this is basically a high level of how embeddings work. What we are interested in is how do we figure out that two words or two sentences are similar, right? So this is where a few metrics calculations come in. So one of them is cosine similarity. Now, if you had a 2D graph like this, right? If you have a 2D graph like this, it's very easy for you to say, if you draw a vector from origin, one to water, one to let's say, the distance between the angle you form is actually the cosine angle, right? So that is actually called cosine similarity. So when you talk about embeddings or two vectors, if the angle between the two vectors is large, that means they're dissimilar. Or in other words, if the angle is smaller, you can tell that these two vectors are similar in the world of embeddings, right? So what we're going to do is I have a simple script that I've just ran. Now in this graph, it only talks about words. So it's very easy. Like you can say ocean or water are similar. If you had a vector for ocean, the angle between ocean and water would be quite small, right? But how do you deal with this in terms of sentences? Because sentences don't only have words, they also have semantic meaning. Like I'm eating an apple, whereas I'm using an Apple iPhone, right? They're two different things, right? Even though the word apple is there, the embedding model should be good enough to distinguish the Apple iPhone with the Apple fruit. And there are actually embedding models that are out there that are actually trained on sentences rather than just words, right? So let's actually look at a very quick example. Right. You guys can also try this on Collab. I'll just show you how to do it right there as well. But actually, I'll just take you through the example first, and then we can discuss on how this is done. Right. So I have a simple function that calculates cosine similarity. This is basically a normal vector formula that calculates the angle between two vectors, dot product divided by the magnitude of both vectors. Right. And I have a few questions and I have a few sample. Right. What do I eat? What's the battery life? Which phone do you use? And my sample is I'm eating an apple, I'm consuming an orange, I'm using an Apple iPhone, right? Now let's actually compute embeddings for each one of these sentences and also see what their cosine distance is or their cosine similarity is, right? And this code is available in GitHub, by the way. The GitHub link is in the Collab notebook again. So let's actually look at this. Let's actually see this graph. Yeah, this whole thing. Hold on, I might have to zoom out a bit. Cool. Okay, so this is a heat map, but I'll tell you how to read this of sort. So my first question, that is, what do I eat? And my first sample, that is, I'm eating an apple. You can see the square is quite dark, and our cosine similarity is 0.61. So by the way, if the angle is smaller, cos theta of a smaller angle is close to 1, right? So smaller the angle, cos theta is larger. Cos theta is -1 to +1. The smaller the angle, it's closer to 1, right? So that's why you see a larger number here. So in this example, what do I eat? And I'm eating an apple, has a larger number than, let's say, what do I eat versus I'm using an Apple iPhone, right? This sort of tells you that these two vectors are closer compared to the one with the Apple iPhone, right? So do you get an idea of how you can actually compare sentences and come to a conclusion that which sentences are similar to which other sentences, right? So is this sort of like forming in your head, like you can sort of make out something from this? And as again, there are other examples like what is your battery life? Battery life doesn't have any meaning in terms of fruits. So you get a larger number or you get a larger score with the question, what's my battery life? And I'm using an Apple iPhone, right? You get a larger score here, basically. So are you guys understanding this? Any questions you guys have? Is this all clear? Right. No, I'm just taking some random strings. This is just my random strings for demonstration. Yes. So not before that is another step. You have to first chunk the PDF into smaller bits because LLM can't really understand the whole PDF, right? So I think you're getting there already, but we'll come to that, right? So if you had to do this in Collab, I would say you can try out a few sentences or words in Collab and see how those embeddings compare. You can take, okay, there's another metric I'll speak about before you do this. There's something called L2 distance, or in simpler terms, Euclidean distance. In your math classes, you would have come across the distance formula between 2 points, right? Root of x2 minus x1 whole square plus y2 minus y1 whole square. That's called the distance between 2 points. Now that formula also applies to n dimensions, because your vector that is generated by the embeddings models is not of 2 dimensions or 3 dimensions. It can be dimensions of hundreds or even thousands, right? So L2 distance is another metric where you see the distance between two vectors, and that can also sort of tell you if if a sentence or word is similar to another word or sentence. There's another heat map which only plots L2 distances, and in L2 distances, it's the other way around. Lesser the distance, the more similar they are, right? So in this case, you'll see darker squares for dissimilar sentences. Like which phone do you use? And I'm eating an apple. They're quite dissimilar. So you see a darker square compared to a lighter one where there's an Apple iPhone mentioned. I hope that sort of makes sense, right?
If you want to correlate this with the graph which you showed, the 2D graph, I mean, we thought about we'll place an ocean over there, which will be very close to each other, right? So the distance will be small. So just a correlation to it.
So what we can do is, in your collab notebook, you can try a few things out. So let's actually do this. Hopefully you guys ran the installation script. Don't worry if you get this error saying that pip dependency resolver does not correctly, whatever, right? That's fine. Your collab notebook will still work. I'm just going to do a standard import. And since I mentioned these embedding models are machine learning models, there's a lot of companies who are making these embeddings models. There's a lot of research, decades of research has gone into making these embeddings models. So it's kind of tricky to even figure out which model do I use. Do I use a model made by OpenAI? Do I use a model that's made by Meta? There's a lot of issues. We're going to come to that soon, how to address that. But for now, I'm using a model called BG Large English. It's a 1.5 variant version. And actually, for the sake of this demo, I'm going to do a smaller model. They have a small and large. The smaller model is of lesser dimensions, while the larger models are higher in dimensions, so more context is captured. But let's just take a smaller one because it just runs faster, Cool. Let's take a few words.
Yeah, sorry. I mean, can you able to access that? It should be there in your GitHub repo. The same thing, it will be there in embedding.notebook, Jupyter Notebook. So from there, if you want, you can just clone that. Zoom. Can you zoom it?
Oh, zoom in. Okay.
Sorry? Can you repeat? What are the?
Oh, do you want to see which data set it's trained on? Yeah, so if you actually go to, so this model is hosted on Hugging Face. So if you actually go to Hugging Face, let's do BG, large, English, and it'll take you to their website. And if you actually read through their website or their listing, they will ideally have what data this model is trained on. And this is actually quite useful, actually, because if, let's say you had to build a solution around finances, right? You'd probably pick an embedding model that knows the finance terms and finance context better compared to a generalized built model, right? So all these things do come into the picture, but for this demonstration, we're just going to use a generic model. And it's called BG large EN. I'm just using a smaller variant because it's just faster to run again. Right. So I have two words with me. Let's actually generate embeddings for them. So how do you do that? You can just do word one embeddings is, let's just do this model.embed query. What did I do? Oh. Cool, we have embeddings for word one. I'm going to do the same for word two. And then, so if you actually just print out word one embeddings, you see it's a list of floating point values, right? And this is what the embedding model gives you. And you can actually check the dimension of this embedding model. You can just do length, right? So this embedding model gives you a dimension of 384. That means the 384 individual floating point numbers in that array. If you actually use a large one, it'll give you around 1,000. So it's more computationally intensive. But apart from that, let's just copy the code that will actually give us the cosine similarity, the cos theta value. Let's actually print, let's do cosine similarity of word one, comma word two. And we have to actually pass it the embeddings. Cool. So this is the similarity between the words ocean and water. And we're getting a very good score of roughly 0.8. 0.8 is, 1 is the maximum. So 0.8 is pretty good, right? Oh, you want to see the previous code? Well, this all is in the, what do you call the GitHub repository. The examples might be different there, but it's the same code, right?
Yeah, basically, if you want to embed, just use that embed underscore query. So pass in whatever the word you want. So it will give you a vector or a floating point vector for you. And we are just showing that floating point vector. And with the vector, if in case you use any of your vector database, we'll talk about that next. So basically, we'll use either one of them, either the cosine similarity or the L2. Most probably it should be the cosine similarity. We'll talk about it just to give a hindsight before we go there so that you will understand these concepts as well.
Cool. Yeah. No. So actually, if you run this piece of code, it will download the model onto Collab's machine. So you're actually downloading all the weights and the model into your local machine, and it's actually running on your CPU. So that's why I picked the smaller model, because it's less intensive to run. There are, again, cloud-based solutions. You can use OpenAI embeddings. OpenAI has their own embeddings model, and you can use it by paying them a lot of money. So moving forward, so as we saw, like ocean and water have very high correlation, right? They probably are very close to each other, and it just replaces something else. Let's actually do ocean and hockey, and you should see quite interesting results. So ocean and hockey, it's a bit lesser score. It's 0.6. 0.6 is definitely less than 0.8. So you can already tell that there is something going on, that embeddings models are somewhat smart enough to tell us, which words are similar, which words are not, right? And you can also try this with sentences. I'll let that experimentation. I think you can do that experimentation, right? Put in some random sentences and you can try that and see what the score comes out like, right? So cool. Let's go ahead. Okay. Why is my shortcut not working? Okay, cool. So we talked about embeddings, and that is sort of solving our problem of retrieving relevant data for your question, right? So let's actually get to how do you want to, take the data and embed it. So you have a huge F1 document, which is 107 pages, right? Let's just assume for simplicity, it's 10,000 words. There's 10,000 words in the document, right? Now, how do you chunk it so that it's just enough for an LLM to understand, but also not more? Now, if you have a larger chunk, when you embed it, the context is going to be everywhere, right? Maybe one chunk talks about 5 different things. So your embedding model won't be very accurate, right? In terms of denoting what everything means in that vector. So the goal is you use very small chunks. That is, you take very few sentences, and that is your chunk size, right? Probably a good number we can start off with is around 500. So every 500 characters, not words, 500 characters is one chunk, and when you embed that chunk, you get a vector representing those 500 characters, right? Before we go there, I'll just show you some of the popular methods that I use to chunk a data, chunk a file. So a very quick demonstration here. So document loaders. Okay. So for this demonstration, I have another file called story.md. It's a markdown file, and I'll show you why I have taken a markdown file here as an example. But this is basically some random story written by ChatGPT for me, and I'll show you how why this is useful, right? So this is the contents of a file, right? Now let's look at the most basic way of chunking, right? There's a chunking strategy called character chunker, where I explain, you just tell it, hey, I want only 500 characters in a chunk, and it's just going to do a very naive chunking method of, like as long as it finds 500 characters, it's going to put them in one variable or something, So a page of 10,000 characters is going to be chunked to 500 each. So you're going to end up with 20 chunks in that sort of sense. Right? That's like the most basic chunker, but there are better ones. People have done a lot of research and come out with better ones, and this is one of them, called the recursive chunker. So the recursive character chunker, what it basically does is, let's say you take a chunk in between, right? There's a chance that the data you need in that chunk is also available in the previous chunk and the next chunk as well, right? You might not always get all your data in one chunk. So what the recursive chunker does is it takes some characters from the previous chunk and the next chunk and also includes it in the chunk. Right? So you guys get this? Huh? Yeah, this overlap. Yeah, it's actually called overlap, right? So you give a fixed number of fixed character size plus some overlap, the maximum overlap that you're going to add to from the previous chunk and from the next chunk, right? And I have a small script to demonstrate that. So I'm using a recursive character text splitter with my chunks as 256 characters and 50 overlap, right? And I just have some very nice formatting going on here. So every time you see a change in color, it's a new chunk, right? But there's some very interesting things that are happening here, which we have to see, right? Now the question arises is, if you chunk everywhere possible, like if you just chunk at the hard 256 character, you might end up with broken sentences, right? Broken sentences is ideally not something we want. So so since we're using a library called LangChain, it's also there in Java, don't worry. So the recursive chunker in LangChain is built to not split at a sentence, right? So as long as a sentence completes, that whole sentence must be in a chunk. If the whole sentence does not fit in the previous chunk ends right there, and the next chunk is started, right? And there's a few delimiters, not only when a sentence ends, but new lines, exclamation mark, question mark, or two new lines. They sort of mean that the chunk might end here or should end here, right? So that's why you might see a few chunks that are only two lines, and some chunks. This is actually the full 256 because this is actually a new sentence. But there's no exclamation. There's a new line here, so there's a new sentence right here. And this whole thing is actually one single sentence because there's only one full stop here. So the green line plus the red sentence probably would be more than 256 characters. So that's why I didn't include the green one along with the red sentence. So you sort of get the idea that the library is actually trying to not trying to break sentences apart, which is actually quite useful, right? But you also end up with things like this sort of stuff where you have only one line in a chunk, right? Which is not something. It can be useful, may not be useful, right? So we'll actually explore some other ways, right? And I'll give you a hint here. This markdown file actually has headings, right? It has heading 1, it has heading 2. So 2 pound symbols is heading 2. And it has multiple heading 2s, right? So wouldn't it make sense if you actually split at headings and retain whatever comes in that section as a chunk, right? Is that possible? You can actually do that. So there's something called specialized chunkers. So you can apply chunking strategies, special chunking strategies to different types of files. So in this case, there's a markdown example. So actually, let's just directly go to the what we can see here. So again, every time there's a change in color, it's a new chunk. So you can see here, the whole first section falls in like one chunk, whereas the whole second section falls in another chunk. Because if you see the rules of how we told it to chunk it, we told it that whatever comes under heading 2, put everything in one chunk, right? Now, this might be important because your title of that chunk might actually convey information that might be useful for you to derive an answer, right? Is everyone on the same page? Is everyone getting this? Now, you might also end up with situations where you can see this particular chunk is quite large, right? Like this is definitely way over 256 characters. So what's the solution right here? So what you can do is you can apply a recursive chunker on top of a markdown chunker. So you will chunk inside only this markdown section, but you have an advantage. You get to preserve the heading, right? You can also add the heading to every chunk that you generate. It sort of preserves the heading in every chunk. We're going to talk about metadata later, but all these are sort of optimizations, right? So let's just quickly go through this and let's get to data paths. So yeah.
Yeah. So if you are in with us, so we are still, we assumed we just took one question. We went to the chat GPT just to recall. We added one question. We gave the entire context that did not give us. Then what we did was we will actually check those things. So that is what it is. So basically as part of the RAG pipeline. So there is a query, there is a question which you will ask for. Underneath what it happens is it will chunk the data for you. So we just spoke about what's the chunking, what are the different strategies of it. Okay, and then we'll talk about briefly touched about embeddings, which we have already seen with the 2D graph, how it will be. Okay, so once we have the embeddings, then we'll talk about what are the, like how you have it in any of the programming language or whatever the code which you do, right? You can't keep everything in memory. So somewhere we need to persist it. Somewhere we need to store things so that at least we'll be able to retrieve it. So like how we have our relational databases in Java or the NoSQL databases like Mongo, all those things. So similarly for all these embeddings, whatever it's been present over there, we need to store. We need to store those vectors somewhere. Okay, so that's where the vector stores are. Vector stores will come into picture, or vector databases will come into picture. Okay, so just to understand that in some brief with a real world analogy, just treat the diagram over there as your library. Fine, so you have a library. Assume in the library all the books are been it's in different order. I mean, you can't find, if in case I want to go pick a book related to machine learning, or pick a book related to say virtual threads, or anything related to the vector APIs. If it's been disorganized, how will you go and pick those books? How will you go and get those books? I mean, you can still get the book, but it will take hell lot of time. It will take huge amount of time to go and figure that out, right? So if in case it's been organized, let's assume it's been organized, which usually we do in our any of the libraries which we go ahead. So it will be organized in a section telling that, okay, something related to machine learning, something related to Java. There'll be a separate track altogether related to that specific field, or some books related to physics, right? So if those things has been ordered together, or those books has been grouped together, then it will make, as a user who goes to a library, or as an end user who is building this RAG pipeline to pick up those related contexts or related vectors very easily. So that's where the vector stores are. I mean, that's where the vector stores will play a big role in it. And similarly to the vector stores, like how we have our index, right? So we create a primary index, secondary index, all those stuff. So even in the vector databases, there are indexes. Okay, so we'll roughly talk about four indexes. We'll just see how it is. What is the basic one? So basic one will be as simple as there's something called flat. Should we go there? Or?
No, I think so. Flat is basically no index.
Yeah, sorry, go ahead.
So the prompt is the very end. Like first you need relevant data, right? This is a prerequisite.
Yeah. So this is the prerequisite to get the context. So basically, let's assume there's an employee database. Okay. So the query is to fetch a specific employee ID. That's the question, right? So, I mean, to that we will form the actual SQL query. Let's assume it's in SQL. So we actually form the SQL query. Assume forming of SQL query is your prompt. Okay. So the prompt is still at the other end of it. We are just talking about just the question. The question is to fetch a specific details of the specific employee. Okay, so that's the question. To fetch it again, I mean, since it's a huge employee database, so we are storing it. Assume that correlate with the vector store. We are just storing it in the vector store. Maybe to store it, it can't be a simple normal word. I mean, simple things like how we store it in relational. It will be something related to the floating point numbers is what I need to store, which is the vectors. So once we go there, post we retrieve, then we'll talk about the prompt part. Make sense?
Yeah.
Yes. So this is the complete RAG pipeline, like how to build a RAG pipeline is what we are going to do it. Okay. So,
Yeah.
yes, it does. We'll talk about that. So basically there are two things here. So one is we wanted to make you understand these concepts in the RAG pipeline. So to build the RAG pipeline, I mean, you need to know few things. So that is what we are focusing on. So first is to understand those concepts, and then last we'll just stitch them all together and then see for a given question, whatever we ask the same thing, we'll ask it once we build the complete RAG pipeline, and then see whether my chat GPT or Gemini or Olama, we'll talk about those things. How will that answer for us?
Cool. Just to reiterate, vector stores and indexes. Like Lohith gave an example of a library, right? So if you walked into a library which is organized, you know where to go. Like you want a physics book, there's a physics rack right there. You can just walk to the physics rack and pick your book, right? Compared to if it's disorganized, you have to go through every single book in the library, right? So you can see the relations. It's like O of n. So if you have one vector, the query vector, and you have a bunch of chunks which are embedded, you'll have to compare that query vector with every single embeddings that you have, right? That's a very tedious process. But what if you could, but since these vectors have meaning, right? They have some sort of meaning, some sort of semantic meaning where you can group vectors together based on how similar they are. And that's where vector databases come in. It's not only vector databases, but the indexes are the main thing. You can store data in vector database and still do the O of n search. But the indexes are the most powerful thing in a vector database, because the indexes will make sure that similar vectors are kept together. So when you query, you don't have to query across all the vectors in the database. You can directly go to a place where you think the similar vectors are present and just do a query over there, right? I hope everyone understood like why we should be using vector databases and why indexes are very important. Right? And I have a small, this is taken from, okay. So, so this is a small chart again, right? So flat you see here is basically no index. Flat basically means you're comparing the query vector with all the existing vectors, right? And the number of existing vector will be in millions. Like, no customer is going to come and ask for a RAG solution on one document, right? It's going to be probably hundreds or thousands of documents that you have to do. You have to build a RAG on, and you're going to end up with the millions of vectors, right? It's not very efficient. So there are a few methods here. We won't go into details of them, but I'll explain what IVF is. So inverted file index. Does anyone know how k-means works, or the clustering algorithms in machine learning? Right. So you cluster similar points together by taking a centroid, right? So IVF sort of works in the same manner, where you have a centroid vector and you sort of set a threshold, and around the threshold, all the vectors are similar to the threshold vector. So when you query, you only query against the centroids, and if you get a matching, or if you set some threshold value, like let's say my match with a centroid is 0.6 and above, then I will go deeper into that cluster, right? It's that IVF is a very basic indexing mechanism. There are others. HNSW, this is a very complicated index, but we're going to use HNSW, but I won't go into details of how HNSW works. Or quickly, I can just tell you how it works. So you have a bunch of vectors, and what HNSW does is it builds abstractions of your vectors. Think of it, you're summarizing 100 vectors into 10 vectors. And then you're summarizing those 10 vectors into 5 vectors. And then eventually you summarize those 5 vectors into 2 vectors, right? So you get summaries of all the vectors as layers of abstraction. Now your query will only go to the topmost layer, which has a summary of all the other vectors. And then if it does a good match, then you'll go deeper. So that is basically how HNSW works. It's again very complicated, so we'll not go into details of it. But this chart is just to demonstrate performance metrics. So before we actually explore this, let's recall. So what is recall? Recall is basically, you can say accuracy. So one is 100% accurate, 0.85, 85% accurate. So recall is basically accuracy, okay? So in flat, when you don't have an index, you're searching through all the documents, your recall is the highest because you're not missing any single vector or any potential vector that could be your answer, right? So that's why recall is 1. But if you actually look at the query time, it's almost 18 milliseconds. These metrics are done on a specific machine for a specific data set. So take the measurements as relative, right? We'll only take relative measurements from flat. So if flat takes 18 milliseconds and you compare it to something like HNSW, right, which takes just 0.6 to 2.1, that's like almost 15 to 18 times reduction in speed, where you're still getting a decent recall rate. Now you might be confused why the recall is not 1 here. That's because you are grouping similar vectors together, and that grouping can go wrong, right? You can always miss a vector and not group them together. So you're not comparing all the existing vectors. You're only comparing some vectors that you assume are similar to your query. So there is a chance that you might actually miss out some vectors that are very similar. That's why the recall is not 1, but this is still acceptable. You're still getting a 15 to 20 times boost in performance with a decent recall rate, which is 50 to 95% accurate. Right? It is still acceptable for us, right? Again, there are other indexing methods. Again, we won't go into details of them, but HNSW is what we'll be using for this demo today. Cool. Right. You want to talk about the basic, right?
Yeah. So again, coming back, so we were provided a query. What are the question? What does the blue flag means, or what does blue mean in an F1 document? So with respect to that, we talked about what's chunking. We talked about embeddings. We talked about vectors. We talked about the vector store. Okay. Then finally what? So once it's a vector store, then finally it's about retrieving that information. How can I retrieve that? Whatever the question, based on whatever the question user has asked for, how can I retrieve the documents? Right. So we'll talk about retrieval part now, followed by which we'll talk about the LLMs or the generation part.
There's a bit of a misleading thing here. There's a small mistake in this diagram. And retrieval only comes from another question. So this part is not query, it's document.
Yes. Yes. During your ingestion, whenever you get a document, so okay, the prerequisite is I need to embed those documents based on which I need to ask a question for. Okay. Or if the model is already trained on some set of documents, which will again be embedded and stored in an vector store. Okay. They can use any of those indexes which has been mentioned. So there are a few popular things like ChromaDB, Quadrant, Milvus. You can go to any of those vector stores and you can actually in the documentation, you can see which particular index it's using. If not, you can override the index according to your use case as well.
One thing to point out in RAG is it's heavily experimental. Like one RAG solution to a particular set of data might not work well with another set of data, right? So RAG is highly experimental. You need to experiment a lot on which queries are working well, which queries are not working well, why are they not working well. You can play around with embedding models, chunk sizes, etc. There's a lot more what goes into this. We'll talk about a few optimizations later as well. So yeah, but to do retrieval, you first need to have some data. So that's like the starting part right here. So again, this is not query, this is document. Left hand side is document. Yeah, right side. So when you only have a query, that's the retrieval. So we'll just walk through a very quick demo using a vector database, taking a document, chunking it, embedding the document into a vector database, and asking some questions on it. Let's do that actually. So for this demo purpose, I'm using something called ChromaDB. It's a very popular open source vector database. The only reason I'm using ChromaDB is because it also has functionality to work like an SQLite database, where it creates a local file. It's not like you have to run a Docker container, server running. So it's just easier for demos, and if you use a Google Colab, they'll just create a file on the machine. You don't have to run a server. So that's the only reason why we're using ChromaDB. Cool. Let's see. Okay, cool. Let's get started. Doing the necessary imports. Let's do JavaFest. Okay. Before I go into vector databases, they also so in relational databases we have something called tables, right? So each table has some sort of data in them. In vector database, it's called collections. If you are aware of NoSQL databases where they have documents and collections, it's basically the same thing. You have a collection, and in a collection you can drop in some embeddings. It's the same. It's pretty much the same thing, right? So I have a collection called JavaFest drag cosine. I'm just going to execute the cell. So once I do this, oops. Yeah, once I execute the cell, hopefully I should see. So there's a folder called Chroma right there, and you can see it created some local files to store my collection. Right. So this is because I'm using something called a persistent client. Persistent client basically means it's going to just use your local system file to store data instead of a server running on a Docker container or some other machine. Right. So cool. And yeah, so just a few things here. I'm using cosine similarity as my metric with the HNSW index. Cool. And currently my collection is 0. There's nothing in my collection. So let's actually add some data to my collection. So let's actually load the F1 document right here. So don't worry about loading part. There's a bunch of loaders that you get access to. One of them in Python is called PyMu-PDF. So PyMu-PDF basically takes a PDF file and gives you output as markdown format. So if a PDF has headings, it's going to put them as H1, H2, or the markdown equivalent of those headings. And if there are tables in let's say PDF, it's going to put them as markdown tables, which the LLM can understand really well, right? So again, if you're worried about how this can be done in Java, Java has wonderful libraries for extracting data from PDFs, or there are other there are cloud providers, there are cloud services that only specialize in extraction. And there are actually a lot of them. AWS has Textract, Azure has Documents AI extractor. There's some other third-party services such as Unstructured, Llama Parse. All of them should be there. We'll provide a list of all of them later, right? So cool. So once I have the markdown data, this is my markdown data, right? And this is basically all my document, right? And if you actually print, let's print length of. So this document has, let's see, it's roughly 3 lakh characters. Roughly 3 lakh characters this document has. So let's just apply a chunking strategy. I'm going with a very basic recursive chunker here. I'm not even doing specialized markdown chunking. So after chunking, I end up with 776 chunks, right? Now let's embed all these chunks. So this is a bit of a syntax for ChromaDB. So ChromaDB does embedding under the hood. It uses a model called, I'll show you the model it uses as well. Okay, before that, I remember when we talked about which situation you would use which model. I mean, I'm talking about embedding model. So if you actually, there's a useful page you can look at. It's actually called Hugging Face Leaderboards. It's right here. So Hugging Face has this page called Leaderboards or MTB Leaderboards, which actually ranks all the embedding models based on the performance, right? But this performance is generic, like it's not domain specific. And if you actually go to Retrieval, you see a bunch of models here. And the one for demo we used was, you should see a BG small pop up somewhere here, right? So you get the thing. So there's a bunch of embedding models here, and you can pick up your own embedding model based on your use case. And also performance, because it also tells you what is the dimension of the embeddings. And you can see some models are 700, 300, 500, some are even 1000, right? So more the dimensions, more computation intensive, your cost will go up. So you have to make a like a good choice on which model to go with. You want the cost to be low, but you also sacrifice some part in the semantic accuracy the model provides, right? But these are all trade-offs, right? It's fine. We can work with these trade-offs. So ChromaDB uses a model called all mini LM L6 V2. It's another embedding model. It has a dimension of 384. So the vector that's generated will have a length of 384 floating point numbers, right? And it does it under the hood. It doesn't actually show us how it's embedding. Since we already had the embeddings demo, so you can do the same thing and also pass it the raw list of floating point numbers as well. But this will do it under the hood. And we'll just give it some time. Meanwhile, if you guys have any questions, we can take them up. Okay, so now you have your document chunks, and each chunk represents some part of information. Now we have your query. Now you will embed your query as well, and then check which embedding of the document matches more semantically. Yeah. Yes, it's actually called similarity. Yeah, and we're using the cosine metric. Some applications might use Euclidean distance. That's another one called inner product. So there's a bunch of metrics and indexes. So in our case, we're using HNSW index with cosine metric. Yeah. Again, it depends. It's mostly on experimentation. You have to experiment which one works well.
Yeah, and also if in case you are dealing with some kind of a data which is less dimensions, so then it will make sense. So again, the L2 distance is based on the direction, based on the magnitude or the distance between them. But the cosine similarity is based on the angle. So wherein if given a more robust, usually in most of the cases, whenever we are building the rack pipeline, so it will involve huge amount of documents, maybe a law book or something wherein they need to check for a specific section of the IPC code or some related things related to it. I mean, some kind of a use case which will be way beyond more than that. During that time, they'll use it. So, I mean, usually most of them will go with a cosine similarity. That is what they recommend from the data science practice as well, to go with the cosine similarity than the L2 distance.
So when the embedding model is trained, it will definitely use some of this data to retrain itself, because these embedding models are trained on large amounts of data, right? So there's constantly a feedback loop going to retrain. It can be a manual feedback loop. Maybe an external auditor is saying, hey, this makes more sense. Like, if you think about how large LLMs are trained, some LLMs can be manually, there's manual auditions. Like basically, if the way ChatGPT is done is you give it a bunch of questions and it generates a bunch of answers. And then a person will actually go there and say, this is right, this is wrong. And then that'll go back into a retraining loop. That's manually done, but there are ways to do it automatically as well. So that sort of method might be employed. But this is mostly going into how machine learning models are trained, because this is a pure machine learning model, which we are just utilizing. Right. So looks like our documents are added, and cool. Now our collection has 776 objects, which are basically embeddings or the chunks that we have embedded, right? Now, how does retrieval actually work? Now you have your database full of embeddings or collections, and now you have your question, right? Now you're going to convert that question into an embedding as well of the same dimensions using the same embedding model, right? Because if you use different embedding models for adding documents and querying, the semantic score might actually go wrong there, because one embedding model might give a different value for the same context. So use the same embedding model for query and documents. So we're going to convert a query into an embed or into an embed, basically vector. And then we're going to run similarity search between the query vector and all the vectors in the database. And it's actually going to use an index rather than running it like a brute force approach. So using this is actually abstracted. You can just all this is actually abstracted under the hood. If you go under the hood, it's creating an embedding and actually comparing it with the vector database. So let's actually see our results. Cool. So we actually have our results, and for this Chroma SDK, the results are sort of this fashion. So what we're interested primarily is documents and distances. Cool. Let's actually see what's happening. One more thing, if you actually notice, this is ranked from lower to higher, right? But in cosine similarity, we know that higher is basically better, right? Smaller the angle, larger the cos theta. So that means they're more similar. But what generally vector databases do is they give you the value with 1 minus cos theta. So if higher the cos theta value, they do 1 minus and then give you that distance, because it's just more human-centrically readable that smaller the value, more closer they are. Like the distance between those two is smaller, that means they're more similar. So they generally vector databases employ 1 minus cos theta rather than just cos theta. That's why you're seeing values that are lower ranked first, right? And we have all our documents, right? Cool. So let's actually print all these documents as text and see where this takes us. So this is basically all our chunks returned back by ChromaDB, right? And this is significantly less than what the entire F1 document had, right? This is only a few characters long compared to the entire document. And you can actually test this out. So what you can do is just take the context. Let's go back to our ChatGPT. Oops. Where is this? Cool. And I'm going to modify this thing, right? I'm going to be like, I'm going to remove all the existing text and place the context we retrieved from the vector database, right? And then play. Oops. Cool. So it looks like it did answer. It says the blue in the provided context refers to the blue flag or flashing blue light. Basically warns drivers that there's a faster car approaching. Looks like it did pick up the answer from the context we provided. And if you actually go, let's actually look at the context we retrieved. Right. And if you actually just search for blue flag or just blue, you'll find references like blue flag, blue blah. So there's a lot of things that are actually relevant to what we're actually searching for. Right. So this retrieval sort of works for us, right? And it's actually working out. And whatever step you saw us doing right here, like the prompt with the context and the question, this is the last part of your RAG application. So once you retrieve the documents or retrieve the relevant chunks, you pass it to an LLM saying that, hey, this is my question. This is the context that I think is relevant. Only pick the answer from this context if you can find one. That is basically the last part of RAG. That is a G, that is generation. And usually it's not done in this fashion. It's usually done using an API. You probably get an open API key, and using their APIs, you fire a request and you get a response, right? No one's going to manually go and put things on a ChatGPT console. It's just easier to present, that's why. But yeah, so if you had to try this, right, you already have the code for adding documents to a vector database and retrieval part as well. If you talk about generation, we'll just touch on a few popular methods or popular LLMs out there. For those of you running Macs with M chips, not the Intel chips, but the M chips, and people with good enough CPUs or GPUs, there's a tool called Olama. It lets you run LLMs locally on your machine, right? So there's a logo it has, and you can run models such as Meta Llama 3, Meta Llama 3.1, 3.2, Mistral 7, Mistral 3. I'm not sure which version, but Mistral AI. And since your laptops are not very powerful, you'll probably go with a quantized version of the model or a smaller model. Like Llama has 8 billion and 70 billion, but your laptop will probably only be able to run the 8 billion model compared to the 70 billion model. So Olama is a great way for you to do some testing locally on your machine without actually going to the cloud, right? And yeah, it's the parameters. Yeah. And again, you have Google Gemini as well. Google Gemini has a very generous free tier in terms of using their APIs or their LLMs. So you can try that one out as well. And obviously, the most common one out there you'll see is ChatGPT. OpenAI key, and then you just fire a request to the desired model, and you'll get a response back. So that is basically part of the generation. What we demonstrated here is actually a generation, but you will do this in terms of code. And we can show you that. So okay. Okay, so I'll explain that bit. Let me open. Is this? All right, cool. So right now we are only retrieving from our data in the database, right? And that is what we want right now. That's like a RAG pipeline only for our documents. Now you must, if you were part of the previous session that was working with Vertex AI to hit Google Maps API and get data, that is called an AI agent, and you can employ agents to do other things rather than looking through a vector database. So, so what you'll do is if you can't find an answer that is not private to only you or your documents, you can employ a web search. Like if your LLM can't provide an answer, it'll generally say I don't know, or you can actually prompt it. You can tell it that hey, if you can't find the answer in the provided context, just say I don't know, or say you don't have an answer. And then when it gives you that answer, you can actually double down on a web search, and that's actually way more complicated. That goes into how AI agents work, but yes, that is possible. But this demonstration is only for private documents or something that you own and you want to try it out and test it out.
Yeah, I mean, it actually depends. So let's assume you need not share your documents outside. Okay, but in those cases, you can have the self-hosted LLM. You need not go for ChatGPT. You need not go for Gemini. Even if in the terms and condition, even if they mention they'll not play around with your data, they might play around with your data. Okay, instead of that, you can host either, I mean, it's not recommended to host the Olama in the production, but there is something called VLLMs. You can host them in production, which means you can just pin up a bare minimum EC2 instance, go install the VLLM over there. It will run out of it. None of the data will be shared. You can have your own vector database as well. Whatever we talked about is the ChromaDB, right? That's an open source one. You can again have a Dockerized image of the ChromaDB in your own, or the Quadrant or Milvus. All are open source. You can use it. If in case I don't want to use open source, I want to use cloud, wherein I'm okay with sharing my data, maybe something which is related to public, then you can use Pinecone. Again, it's a vector database over there. So again, it depends on whether is my data which is very privacy. I mean, is there anything which is privacy to it? I need not share it outside. Then you can host it in your environment itself where it will be more secure. If in case you don't care about, it's okay, it's a public data, I can just share it with outside world as well. From that, I want to analyze some data or the finance documents. I need to see how my year went based on the last 4 quarters and all. So in that case, you can go ahead with the ChatGPT or the Gemini or any of those generation models as well. So, I mean, again, depends on the use case. So we used it, we wanted some of the data to be internal. It need not be shared outside. So we hosted everything in our machines itself in the AWS. Even the Chroma as a Docker, the VLLMs, everything was hosted in our vicinity itself.
No,
Yeah.
ChatGPT won't do any of that for you. Yeah, that's only for one file. But imagine you give a lot of files. I don't think it's maintaining. You can actually try it, right? You can actually upload like 100 documents and see if it's actually retrieving it really well. But what I said earlier is RAG is a very heavily experimented setup, right? One setup of RAG might not actually work with other applications. Like I'm building a RAG for internal documents. It might not actually work with public documents, right? So this is why you'll see there's no one company out there where their RAG solutions are like the top class. Like they'll be like, come upload your documents and you can just chat with them. Maybe some claim to be, but actually there are a lot of edge cases where things can go wrong. So it's actually very important that you build your RAG application specific to your use case, right? And I'll give you an example of a similar project we had. I'll take a similar example where you have a law book, like India's constitution, which is probably around 10,000 of pages, right? And let's say you want to chat against it, right? You want to ask, see, things like Keyword search will work for things like IP numbers, section numbers. But if you ask a question like, what is the punishment given to someone who probably does theft? Your keyword search is not capable of that, but your RAG system can do that because it can take the semantic meaning of your question. And if you do your chunking right, and there's probably a chunk out there that is probably matching with your query. And then that is given to an LLM to synthesize it in a human readable answer. So that is basically where RAG shines, right? So those sort of applications is where you would use RAG. It can be public or private document. That's totally fine. A government organization can also employ RAG. So you don't have to go through their website to look for a bunch of information. You just have a chatbot over there, and then you just ask whatever you need, right? No.
No, we are not fine tuning any of the model. We are just leveraging the, in this case, yeah, I mean, in the Olama case, we are just using Llama 3.1, if I'm correct, 8 billion one. So we are just leveraging those models. We are not fine tuning it. We're not going into the feedback loop. We'll talk about that in the optimization part.
If you guys want to try it locally, once you install Olama, so you can just run Olama run. You can run a model locally on your system. You can pick a more less intensive model, I mean, given your computer you have, or you can just say, again, you can just chat with your LLM locally, right? And this is going to respond. So again, if you don't want to use any of the public APIs, you can just stick to something running locally. Right. Cool. You guys have any questions, or then we can move into, or I'll just show you the complete flow end to end, and then we can sit down for questions. And then after that, we'll move to some optimizations and problems that RAG actually has. So yeah, so whatever you're seeing is basically the same thing we did in retrieval. Again, importing ChromaDB. I'm going to call it, okay, let this be this collection.
Yeah, but in this, if you just look into it, there's no concept of embeddings, which we talked about, embed query, all those things, right? So internally, just the collection.query will actually do the embedding for it. Okay, so if you want, you can even pass the embedded text as well. That should be still fine. But yeah, I mean, so many things will be abstracted. That's the reason we just wanted to take that out and then show you how exactly it will be embedded underneath, so that at least you will be connected to it.
Yeah. So you can see an example prompt I have here. Hopefully it's visible. But your prompts will sort of look like this. It'll be like, answer the question based on a given context only. If you cannot find the answer in the context, just tell that you don't have an answer. Now this piece of this last sentence is actually very important, because right now we're playing around with an F1 document which is public, right? So LLM might already have that knowledge about what a blue flag is, right? So it might actually answer from its own database or its own knowledge, right? Which is something you don't want. So this last sentence is actually quite critical, right? But there are still situations where an LLM can hallucinate. So hallucination is the process where it is not getting an answer from the data you give it, or is using its own knowledge base, right? That is basically hallucination. And there's actually a lot of problems like this. We'll discuss a few right now. Before we move ahead, do you guys have any questions? Cool. Do we move to valuation?
Yeah. So, I mean, now roughly you have seen how the actual generation can be. I mean, how do you build the entire RAG pipeline? Then also he touched based upon the hallucination part as well. So how do you measure? I mean, you can't tell someone, okay, I have built a beautiful pipeline to you. You go ask any question. I have embedded all the documents which are given across tons of documents across the company. I have just across the organization I have embedded. Now anyone can go and ask anything. It will be able to answer. How can you actually give some assurity? How can you actually trust it is giving you a meaningful result, or at least to some extent? How is it giving, right? So usually in most of the things, in any of them, we do something called evaluation. So basically you will evaluate your system to see, or you will benchmark. If you're taking about any Java application, you'll benchmark to see how long it can scale. If in case I want to see which pod is going down, which resources which I need to come up, all those things. Basically you'll do a performance testing kind of a stuff, right? So similarly here as well, you will do something called a evaluation. Okay, so again, there are frameworks here for RAG to evaluate. Okay, so there are two such very good frameworks. One is TrueLens and Ragas. Okay, there is script for this also related, what and all it will evaluate. Okay, it's there in the notebook as well. I can take a look at it. Yeah, mainly focusing on three aspects. It has multiple metrics it will focus on. So one is the groundedness. That is what he talked. I mean, basically it's like, if I ask a question, I need to get an answer. Like, is the answer which is very fruitful? Okay, so you don't see the word groundedness in those evaluation. You'll see something called fruitful, whether I'm getting a fruitful result back to me. Okay, and then it can go wrong with respect to the context. So whatever the context which you are retrieving from the retrieval or from the database, let's assume you have not used a good chunking strategy. Okay, due to which it has not embedded properly. So I mean, basically to the LLM, whatever the prompt which is showed, it had a prompt template, it had a question, and it had a context. So if I don't give the context properly, what is my context relevance? Is the context going properly to the LLM? I can evaluate to that and I can get a score. Okay. So similarly, once I get a context, then what next can go wrong? Is my LLM or the generative AI, whichever I use it, is it giving the answer relevant to me? Okay, so these are the three broad main aspects which you will look into it whenever you write a rack pipeline or that chatbot or whatever you build. So based on this, you will get a metrics wherein you may need to talk to again. I mean, again, you can ask me how will you evaluate against what? So basically, there should be something against which you need to evaluate, right? So yeah, in one of these cases, so you will not evaluate against your, let's assume it's a private data which you're talking about. Okay, so during those times, don't send, or you need to give few questions, answers, and some of the context to it, which you assume, okay, given this question, this is the answer which I'm expecting. Out of this, the answer which my model has given. When I evaluate against an superior LLM or a superior model, roughly most of the time it will be the chat GPT. Don't give your private data over there, because again, I mean, you are sharing your private data with them. Try to give something which is generic or somewhat similar to that is what you can just share, so that again it will go to the chat GPT or the superior LLM. It will get you the context, and then based on that it will compare and it will give you the metrics for you.
Yeah, just to give some more context on where this ChatGPT is coming from. So generally to evaluate LLM metrics, so things like answer relevance, one method is you use a superior LLM and get an answer and you compare it with the LLM you're using. But what if you're already using the superior LLM, in our case, GPT-4, right? Another method to measure answer relevance is you ask the LLM, give the answer, and you tell it to generate sample set of questions. And then you do a semantic similarity with the questions it generated and the user's question. So that sense, you can sort of come up with a relevance score saying that, hey, this answer was given for these set of questions, and it is somewhat similar to the question what the user has asked. So that is one way to measure answer relevancy. Groundedness, as you mentioned, fruitful answer, that is basically hallucination, whether your LLM is hallucinating or not. And for this, you actually need an LLM to validate it. You can use the same LLM. If your LLM has hallucinated, you'll actually give the context and the answer to another LLM and tell it, hey, can you see if the answer from here is coming from the context only or not? So that is basically how groundedness is evaluated. Context relevance, the few methods to verify context relevance. One of them is again semantic similarity, whether your score is quite high or quite low with the query, or you can use an LLM to even validate context. You can ask the LLM, hey, this is one piece of context I got for this question. Is this relevant or not relevant? So that's how you can also re-rank the context you get. These are just a few metrics. But again, there are a plethora of metrics. There's way too many frameworks out there to evaluate. But again, it comes down to how much effort you want to put into evaluation and how much it actually means, right? I mean, one of the best ways to get feedback is actually user feedback. Ask the users to use the system and see if they're actually getting the answers for their queries, right? That's the best thing, right? Okay, so cool. This is the last bit we have. A few optimizations. Again, as we saw, RAG, it's quite simple to build, right? But the thing is, if you go to the real world, especially what systems you have built at Sahaj's, they don't really work out of the box. The basic RAG is something that doesn't actually work. You know, it might answer a few questions, but that sample of questions it answers is actually very low. So there's a few reasons why, right? And I'll actually talk about the first one, that is irrelevant context. Right? Irrelevant context is the vector database is giving you context that is not even relevant to your query. Now that can happen if the chunking or the way you're loading the document or the quality of document loader you're using is not really good, right? I'll give you an example. In some of our applications, there are scanned PDFs, right? You can't really extract text from scanned PDF. You need to use something called an OCR. OCR basically takes a snapshot of it and extracts text using ML and NLP models. So if that model itself is not really good, then you're not actually extracting all the data from the PDF itself, right? So that can also have a heavy impact. The second thing is more on the user's end. What if a user is not asking a very good question? Like it's asking a very vague question, right? So what can you do in these sort of thing? If the question is not phrased very well, then your embeddings will not actually will not be very accurate, right? So generally you will employ something called a query rewriter. You'll send the user's question to an LLM and tell it like, hey, I'm doing this for vector search or vector similarity score. Can you rephrase that question into something I can search on, right? You'll actually use a query re-ranker, which uses an LLM under the hood, right? There's another method called query decomposition. Right? What if a user asks a question which talks about multiple aspects? Like, I want to know what the blue, red, and yellow flag mean. Then your context goes for a toss. Like, you have so much context in one query embedding that it'll be very hard to derive meaningful context from the database. So what query decomposition does is it breaks down one query into multiple queries, only if required. So if I ask a question on what a blue flag means, then it's not going to decompose it because that is actually a very straightforward question. But if you ask a question like what does a blue flag, yellow flag, and red flag mean, the query decomposition step, which actually uses an LLM, will actually give you 3 more questions. It's going to give you each question for each single flag. Like what does a blue flag mean? What does a red flag mean? What does yellow flag mean? You're going to get the answers for all of these independently and then combine them and then give it to the user. So that is query decomposition. It's again, query decomposition again is very, it needs to be tuned because the decomposed queries also needs to be somewhat accurate to your system, right? So again, there's a lot of tuning that needs to happen here. The last thing we didn't touch upon is metadata. So I think we didn't touch upon this, but if you actually see all your vector databases can not only store vectors, but they can also store generic data like your relational database. They can store strings, numbers, or Boolean values, or even some store even JSON values. So metadata here is a JSON field in most vector databases, and it is what it means, right? There is some metadata attached to an embed. And I'll give you a very good example on how this can work out. Let's say you have a bunch of blogs written by a lot of authors, right? And your query is, give me blogs about Docker containers written by some person X, right? Now your query is going to be more heavily emphasized on Docker containers because your embedding model doesn't know the person X, but it knows what Docker containers are. So your query, your similarity search is going to give you all the chunks that talk about Docker containers, even if the person who wrote them is not X, right? So you see the problem right there. So you can leverage metadata when you're adding documents, when you're chunking data, you can explicitly state that, hey, this chunk comes from a blog written by this person, and then you can do a normal filter on it. You can apply an index, a normal relational database index to make it faster again. So it's a few optimizations here. There's actually a bunch more optimizations. There's a lot of resources on how to build RAG and how to improve RAG. There's advanced RAG techniques as well, which we didn't touch upon, but that is, again, it's very advanced RAG techniques out there. You can actually combine keyword search along with RAG as well. There are actually methods to combine your Elasticsearch with RAG, and they sort of give you a combined answer. There's a bunch of things which can be done in this space. I think we've come to the end of the session. I think it was more like a session than a workshop, but again, we wanted to emphasize more on the concepts rather than the actual working part. But again, you guys can definitely go and try out on the Google Colab notebook. If you guys have any questions, we'll take them now. Yeah. A list of, it's a vector.
Numbers, yeah, it's a vector, yes.
No. You can think of it as an array of floats. Mm-hmm. So the author is not any chunk. So we'll give the author as metadata. It's like your vector database can also act like a relational database. So you can use something like, in SQL you write where author is equal to this person. You can do that in a vector database as well. So I'm just saying that you can use a vector database first as a normal relational database, filter down the vectors you want to search, and then employ your similarity search. No. So the blog author will not come in the blog data, right? The author will never be mentioned in the blog content. The blog content is about what the author has written about, but the author's name is never mentioned in the blog content. But maybe when you're consuming blogs, you know who the author is as a separate field, right? So you can add that as a column of some sort in your vector database and do a filter, like a where clause.
Yeah, so basically, as part of the query, you can also pass in the metadata fields. Okay, so there you can pass in the metadata. So there you can tell what is the metadata which I need to look for. That will act as a filter. But before you actually go and check the similarity of the vectors, you'll first look for these things wherein, let's assume there are 10,000 based on the author which has been written. I'll only fetch 10. In the 10, based on this question is what I look for the relevant answers only from this 10. It's like I'm filtering it out from a huge set to a small subset. So filtering. No, no, it's not done by the LLM, right? So you have the question. Okay, so the question will be fed in. So it needs to retrieve. So during retrieve, I'll not go for a normal process of retrieving it, which will give me a cosine related vectors to me. But instead, before retrieving, I will retrieve based on does it contain any metadata fields? If yes, I will retrieve only those things related to that, wherein I'll get out of 10,000, just an example, out of 10,000, I'll get only say 10 chunks or say 50 chunks. From the 50 chunks, I'll apply the normal process of the retrieval part, however the cosine similarity it works for, or whatever the similarity score which we'll look for, and that's how we'll get them in. And then once I get the context, that is my final context, which I'll send it to the LLM. So two-step process. Instead of a normal step, two-step process. First, I'll apply a where class. I'll get very small limited set. Then I will get the cosine similarity or the similarity score related metrics, vectors. And those vectors as a context will be fed to the generative AI or a LLM.
Purely for the developers to take in feedback. So you can ask the people who are using the system, hey, are you getting answers to your question or not? And then what you can do is, so that is, no, that is probably a more complicated approach. There is the concept of fine-tuning embeddings for your domain. But for what you can do now is when you get user feedback, you can actually analyze why that question failed. What is the context you're retrieving? And is the context that is being retrieved making sense or not? Then you know that you have to fix something's wrong in your context. Right? So you can do that with tools such as LLM observability tools, which actually tells you exactly what's happening in your RAG pipeline. They tells you what prompt was fired, what is the retrieve context, what did the LLM generate. So there are tools for those as well.
Yeah, so since here we have used LangChain, so similarly, I mean, there's a wrapper for Java as well, LangChain 4J, you can use that. But also for the observability, which he mentioned, right? I mean, if you want to know how exactly when a question is asked, what and all things it will flow through, like how usually we have observability in the Java world, like if in case you have used Kibana or something, you would have used APM. So when you search for it, you'll get you the traces for that API, right? So similarly, there is LangSmith and LangFuse, if I'm correct. Yeah, so you can use them, wherein you can just get to see, you can just connect it to your local, it's fully running in your local, you can just see those traces as well to see exactly where and all it's happening, what each chunk is getting or what each chunk will give to the next step. So similarly, how we have from the controller to the service to the repository, multiple services to the repository flow, you will be able to see the same traces even here as well. Cool. Any other question you have? The evaluation which we talked about, the context retrieval, right? So that will give you a score. I mean, there is a evaluation notebook as well. So that will give you a score. So based on the score is what we'll get to know, okay, it's missing with the context retrieval part. I mean, during the retrieval part, there is something which is going messier. So just go a few steps back to see whether it's a chunking issue or it will be the document loading, right? So whenever I'm loading a document, it might be an issue over there.